Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 25th lecture of Thermodynamics 2. Lecture 25. So in the current lecture we will be starting the new chapter of power cycles. So the contents of lecture 25 are thermodynamic cycles. So the thermodynamic cycles which we will be studying are divided into two parts. The first part is vapor power cycles and gas power cycles. In the second part, we will be studying gas power cycles. So in the first part, we will be studying vapor power cycle, and in the second part, we will be studying gas power cycle. Then the next topic is steam power plant, ideal Rankine cycle. So in most of the cases, the cycles in which steam power plants are operating are Rankine cycles. So here we will be studying ideal Rankine cycle. So we will study the process that are involved in Rankine power cycles. We will calculate the efficiency of Rankine power cycle. Then we will go through some numerical problem and conceptual question answer at the end of the lecture. Thermodynamic cycles. So the thermodynamic cycles consist of two individual power cycle. So the first one is power generation cycles and the other one is refrigeration cycle. So as you know, the name suggests thermodynamics. So in the previous lectures we have already discussed that the main purpose to study thermodynamics is the conversion of thermal energy into some other form of energy or power. So usually we study all those devices that convert the thermal energy or energy, heat power, heat contents into the electrical or other form of energies. So in the first part, the power generation cycles, so power is generated with the help of thermodynamic energy. So the example of power generation cycle are engines and steam power plants. We have already studied in detail what are the types of different engines and for example we have studied Carnot engine in detail, so we know that how engine absorb energy from high temperature thermal energy reservoir, converts it into work and reject the wasteful energy into low temperature thermal energy reservoir, that is also known as sink. In steam power plants, we have already studied the main components of steam power plant. The main components involved in steam power plants are pumps. It may be a compressor for a gas or heat pump or normal fluid pump. So it will pump the fluid into the boiler in at which the heat will be added to the working fluid, and high temperature high energy fluid will then enter into the turbine. So energy will transfer from fluid into the turbine blade and the blade will start rotating, and the another generator or some device that convert mechanical energy into electrical energy will be connected with the shaft of turbine and electricity will be produced, whereas low energy working fluid will exit the turbine and enter into the condenser. The working fluid that exits from the turbine consists of liquid as well as vapor. So the condenser will reject heat into low temperature reservoir and all the working fluid will be converted into liquid or saturated liquid at least, and then it will feed into the pump. So that is a cyclic process. So in engine, this is an open cycle process, and in steam power plant, it is a closed. Mostly, it is a closed cycle process. Whereas if we talk about the refrigeration cycles, so the basic refrigeration cycle we have already studied. So like steam power plant, the refrigeration cycle also consists of four main components. The main job for the refrigeration cycle is to absorb heat from low temperature reservoir and reject heat into high temperature reservoir. So it also consists of four processes. So low pressure, low temperature working fluid, mostly refrigerant, special type of refrigerant are designed for as a working fluid for refrigeration cycles. So the main components involved in the refrigeration cycle are pump, condenser, expansion valve, and evaporator. So low temperature and low pressure working fluid or refrigerant enter into the compressor. The job of compressor is to compress the gas and increase pressure. So as the pressure rises, so as well the temperature. So that working fluid move to the condenser, and it may be a natural convection or forced convection, and heat from the refrigerant is rejected into the ambient air through condenser. Therefore, the temperature of refrigerant falls, whereas pressure remains same. It is a high pressure. So as after the condenser, it enters into the expansion valve. So there is a sudden pressure drop, and due to that sudden pressure drop, the temperature falls, and the working fluid, that is a refrigerant, will be converted into saturated liquid. Then it is passed through an evaporator through which heat from the cabinet of the fridge will absorb into the refrigerant, and the refrigerant will absorb heat, and the state of refrigerant will be saturated vapor, and that is also a cyclic process. The air conditioning cycle is somewhere same as the refrigerator. So the room is acting as an the refrigerant cabinet. So room will be acting as a low temperature reservoir, and the ambient will be acting as a high temperature reservoir. Whereas function of heat pump is also to absorb energy from low temperature and reject energy into the high temperature. So the somewhere principle is same of refrigerator and heat pump, whereas their objectives are different. So gas power cycles. Working fluid remains in the gaseous phase throughout the entire cycle. Whereas in vapor cycles, working fluid remain in vapor phase during one part of the cycle and in the liquid phase during another part. So in the first part we will be studying vapor cycles. So this is a dual phase cycle or two phase cycle, in which one part the working fluid will remain as a liquid, whereas in the other part it will remain as a vapor, and somewhere in between it may exist also as a mixture of vapor and liquid. Whereas gas power cycles, these are a little simplified form in which there is only gaseous phase, and also working fluid is main working fluid of gas cycles is air, which is also an ideal gas. So if we're talking about cycles, so as I have mentioned previously when I was talking about engine and steam power plants, so I told you that engine operate on open cycle and steam power plant operate in a cyclic manner or cyclic process or closed cycles. So here is another definition of cycle, that it may be a closed cycle or open cycle. So in a closed cycle, working fluid is returned to the initial state at the end of the cycle and it is recirculated. So here the example of steam power plant is given. So the working fluid cyclic motion is given as boiler to turbine, then working fluid moved from turbine to condenser, then condenser reject heat and working fluid move to the pump, and pump pushes or pump the working fluid in the boiler once again. So here you can see that this sequence is a cyclic. So the working fluid return to the initial state. So here the initial state is boiler, and after certain steps or processes the working fluid re-entered into the boiler. So now we will talk about the open cycles. So here working fluid is renewed at the end of each cycle instead of being recirculated. So in closed cycle the working fluid remain consistent and the working fluid quantity may not be reduced, or after some time it may be reduced and renewed, but in the open cycle, after in each cycle the working fluid is renewed at the end of each cycle instead of being recirculated. So here the example given is automobile engines. So here I have already told you in the above that automobile engines is an example of open cycle. So the combustion gases are exhausted and replaced by fresh air fuel mixture at the end of each cycle. So as you know that in the automobile engine, we will study that part in detail, different cycles, auto and diesel cycles. But in the automobile engine, the mixture of air and fuel entered into the combustion chamber. So as the combustion happens, then the chemical energy is converted into heat energy, and that heat energy is utilized or converted into mechanical power or work. Therefore, that after the combustion the air fuel mixture is exhausted and new air fuel mixture is introduced into the combustion chamber. Therefore, this is an open cycle and working fluid or the air fuel mixture will have to renewed after each cycle because it is wasted and all of the energy is extracted from that mixture. Whereas in closed cycle, the working fluid there is no need to renew the working fluid. So the basic uh, now you can see the basic reason to introduce the three different method of thermodynamic cycle was that first you should know whether it's a power generation cycle or power consuming cycle. Refrigeration, in the refrigeration cycle it is a power consuming, whether it's a gas or vapor cycle. So we have already discussed the difference, whether it's a closed or open cycle. So it may be a power generation cycle which may consist of vapor cycle, and it may be a closed power generation, gas, close, and so all these may be a different combination of cycle. So now we will discuss about the steam power plant or vapor power cycle. So this is a schematic diagram of steam power plant. So this is a feed water pump. The function of pump to increase the pressure of the fluid. So here maybe there is a reservoir. Initially water is fed into the feed water pump and pump pushes the working fluid, that is the water, into boiler. So here in the boiler, heat energy is inserted or fed into the working fluid, and water absorbs energy, that thermal energy, and the energy content of water is raised significantly. And after that, there are two exits. So the combustion gases, after the combustion, they will convert into flue gases and they will be exited through the stack into the atmosphere. Whereas high energy water will be introduced into the turbine, in which the working fluid, that was water, and after the boiler phase it will be converted into high pressure high temperature steam. So that steam will transfer energy to the turbine blades, and low temperature steam will be exited out from the turbine. So as the energy transferred to the blade to the turbine, so the turbine blade will start rotated. So the generator is also connected to the same shaft. So the function of generator, it's an electromechanical device. So it will convert the mechanical motion into electrical energy. So here we have thermal energy. Before the turbine, it is converted into mechanical energy, and in the generator, that mechanical energy will be converted into electrical energy. So that electrical energy then will be fed into the grid station and then will be transferred to the homes and different substation as well. So the low temperature, low energy working fluid exiting the turbine will be entered into the condenser. So the function of condenser is to reject heat. So heat will be taken out from the low temperature, low energy stream that is coming out of the turbine and will be converted at the exit of condenser. There will be a saturated liquid, and that stream, that thermal energy that is extracted out in the condenser may be utilized in the to warm up some space or heating purpose, or cooling tower fed into the cooling tower, whose function is to also to reject heat. So that is the working of steam power plant. So ideal Rankine cycle. The Rankine cycle or Rankine vapor cycle is the process widely used by power plants such as coal-fired power plants or nuclear reactor. So the difference between nuclear reactor and coal-fired power plant is that in the boiler section, the heat supplied in the coal power plant is by the burning or combustion of coal, and in the nuclear reactor, the energy supplied in the boiler is the energy that is gained after the fission process, fission reaction. Rankine cycle is a thermodynamic cycle which converts heat into mechanical energy. which usually gets transformed into electricity by electrical generation. So in the previous slide I have already discussed and described in detail the functioning and process of steam power plant. So you have seen that generator is connected to the shaft of turbine, and as the turbine shaft rotated, the generator start producing the electricity, and that electricity is then fed into grids and substations, and then there that electricity is regulated and transferred to the home usage. So the steps involved in the Rankine cycles are: number one is pump. So pump compress the working fluid to high pressure using pump. So pump is a work consuming device. So it will require work input. So the second component is boiler. The compressed fluid is heated to the final temperature, which is at a boiling point at least. Therefore, a phase change occurs from liquid to vapor. So in the boiler, in the previous step that was a pump, the liquid or the working fluid entering and exiting the pump is a saturated liquid, whereas in the boiler a saturated liquid enters, whereas at least saturated vapor or some in the some cases the thermal in a maximum amount of thermal energy introduced, and the working fluid may go into the superheated region as well. So in the least, the saturated liquid will be converted into the vapor phase, that is a saturated vapor. Turbine is the third component. So the expansion of working fluid happens here, and the energy will be transferred from working fluid into the turbine blades. And the fourth component of the Rankine cycle is the condenser. So the condensation of vapor in the condenser occurs where the waste energy goes to the final heat sink. So heat sink may be atmosphere, or that heat that is rejected from the condenser may be utilized further for domestic or district heating as well, or that energy here may be some heat engine may be installed after the condenser, and that energy may be utilized later. Usually it is rejected into the atmosphere. So as we have discussed in the previous slide the working of steam power plant, so the main component of ideal Rankine cycle are same. So for state 1 to 2 we have pump installed. So here we have temperature T1, pressure P1, and enthalpy H1 for state 1. So that is a state 1. Here we have temperature T1, pressure P1, and enthalpy H1. So for state 2, here we have temperature T2, pressure P2, and enthalpy H2. So here we have to remember that energy is supplied to the pump. So WP amount of work is done on the pump, and pump is a work consuming device, and as the pressure increase, so does the temperature. So T2 is greater than T1 and P2 is greater than P1. So here the boiler is connected with the combustion chamber and heat is introduced into the boiler, and the fluid exiting the boiler will have temperature T3, pressure P3 and enthalpy H3, where temperature T3 is greater than T2. So turbine is a work producing device, so Wt amount of work will be produced by the turbine, and fluid exiting the turbine will have temperature T4, pressure P4 and enthalpy H4, and condenser will reject Q2 amount of heat into the sink. So these are the temperature and pressures of different steps of the ideal Rankine cycle. So here are certain assumptions for the ideal Rankine cycle. So the cycle does not involve any fluid friction. So here we assume that there is no fluid friction involved. Therefore, the working fluid does not experience any pressure drop. So this is a fluid friction, means this is a fluid, the pressure will does not drop as it flows through the pipes. So the pressure will remain same, and the there will be no pressure drop when the fluid working fluid is flowing through the pipes or devices such as heat exchanger, boiler and condenser. So in the previous slide, where I have written P2 and P3, so as there is no pressure drop, therefore P2 and P3 will be equal, and P4 and P1 will, there is a condenser between P4 and P1, and we have assumed that there is no pressure drop, therefore the value of P1 and P4 will be equal. I will write here that value of P2 is equal to P3 and P4 equals P1 according to the first assumption. All expansion and compression process take place in quasi-equilibrium manner. So we have already studied quasi-static process and quasi-equilibrium process. So these are very slow process that performed in a slow manner. The pipes connecting the various components of system are well insulated and heat transfer to them is negligible. All components in the Rankine cycle are steady flow devices. So we have already studied about the steady flow devices. Therefore, the change in kinetic and potential energies are negligible. So the steps involved in the ideal Rankine cycles are, so these are the name of the component. So first component is pump, then the next component is boiler, the third component is turbine, and the fourth component is a condenser. So for state 1 to 2, it is isentropic compression. So isentropic mean entropy remain constant. S remain constant. So constant pressure heat addition in a boiler. So constant pressure, it means that is an isobaric process. So in the turbine, the process is also isentropic, therefore entropy will also remain constant here. And condenser, there is also a constant pressure heat rejection. So isobaric. So here we have two isentropic and two isobaric process in the ideal Rankine cycle. So if you may remember that when we were discussing about Carnot cycles, there were two adiabatic and two isothermal processes involved in the Carnot cycle, and now when we are discussing the ideal Rankine cycle, we have two isentropic whereas two isobaric process. So in the pump, this is an isentropic process, boiler isobaric, turbine isentropic, and then condenser is also an isobaric process. So on the right hand side, you can see the schematic diagram that was shown in the previous slide as well of the ideal Rankine cycle. So we know the steady flow energy equation. So Q plus that Q is the heat content, heat energy that is entering, plus enthalpy at the inlet, enthalpy at the inlet, work done at the inlet, plus Q out plus H out and work out. So heat that is exiting, enthalpy at the exit, and work output. So here we have neglected the potential energy and kinetic energy. So change in kinetic and potential energy are neglected here. So that is schematic diagram of ideal Rankine cycle, and that is a TS diagram of ideal Rankine cycle. So here you can see from 1 to 2, this is isentropic process, so the value of entropy will remain same. So here this is the S1, that is S2, S1 and S3. So S1 is equal to S2 and S3 equal S4, and 2 are isobaric process, therefore the pressure 2 and 3, P2 is equal to P3 and P4 equals P1, so P1 equals P4. So So if we know two entropy value and two pressure value, then we know all the pressure and entropies value as well. So here you should know that these are the in the TS diagram the trend of constant pressure line is upward. So these lines in blue and green color are constant pressure line. So from 1 to 2 this is an isentropic process. From 2 to 3 this is a constant pressure heat addition. So that line is a constant pressure line. In the from 1 to 2 in the initial state of 2 it is a saturated, it's a liquid. As heat is added it moves to the saturated liquid line, then there is a heat addition. So latent heat will be added into the working fluid, and working fluid will change in from liquid to vapor, and you can see that it crossed into the superheated region in the state 3. And then the turbine, so it is an isentropic process from state 3 to 1. So heat, there will be an expansion and heat will be transferred from working fluid to the turbine blades. So from 3 to 4 it is also an isentropic process, and at state 4 you can see the working fluid is now in the saturated vapor region. So from 4 to 1 it is a condenser, so Q amount of heat is taken out, rejected into the ambient, and from 4 to 1 there is also a phase change from saturated vapor to saturated liquid. So this is a cyclic process, and as I have already told you in the previous lecture as well, the cyclic process that are in the clockwise manner are work producing devices. So ideal Rankine cycle also is a work producing cycle. So it is a cyclic or clockwise manner, and the process that are in anti-clockwise direction are work consuming process. So now we will discuss one by one the process of ideal Rankine cycle, the mathematics involved in each process. So we have already discussed the steady flow energy equation for the entire process. So in process 1 to 2, that is an isentropic compression in a pump. So here no heat enter or leave the system and no work is output. So no work is extracted, whereas only work that is entered into the pump is a pump work. So enthalpy at the inlet plus pump work is equal to enthalpy at the exit, and pump work is equal to H2 minus H1. Also for open system, the value of work done is integration V dP, that is W is equal to V P2 minus P1. For process 2 to 3, the energy equation is shown, and the process 2 to 3 is a constant pressure heat addition in the boiler. So W in is equal to Q out is equal to W out is equal to 0. So there is no work input and output in the boiler, and no heat is ejected in the boiler, only heat is supplied to the boiler, and that heat is U1. So so I have already told you that the enthalpy at state 2 is H2 and enthalpy at the state 3 is H3. So Q1 is equal to H3 minus H2. That is the change in the enthalpy. So at state 2, the fluid enters into the boiler. So heat is supplied. So this is a constant pressure line. So the zigzag line or upward trend of in the TS diagram is the constant pressure line. So the heat is added and pressure remain constant, and that is a liquid. So it will first convert into saturated liquid, then there is a phase change and it will be converted into saturated vapor, and then heat is supplied again, and at the end of the boiler the working fluid in the superheated region. Ideal Rankine cycle 3 to 4 is an isentropic expansion in the turbine. So here you see the working fluid is in the superheated region, and from 3 to 4 it is also an isentropic process. So heat is extracted and transferred to the turbine plates, and mathematically, so there is no heat input or output and no work input. So the turbine work extracted is equal to the change of enthalpy from state 3 to 4. So for process 4 to 1, it's a constant pressure heat rejection. So the heat is rejected through the condenser, and the amount of heat rejected is Q2, that is equal to H4 minus H1. So in the TS diagram, you can see that from state 4 to 1, this is a also the constant pressure line. So for from 4 to 1, the heat is rejected and the saturated vapor phase will be converted into saturated liquid. Now we will discuss about the efficiency of ideal Rankine cycle. So the efficiency of is given by W output divided by work input. So in the efficiency of ideal Rankine cycle is W naught divided by Q1. It's a cyclic process. Therefore, all the Q's and W's, so there is one heat addition and heat rejection, work produced by turbine and work consumed by pump. So W net is equal to the difference of turbine work and pump work, and W net is equal to Q. So Q1 is entered into the through the combustion chamber into the boiler, and Q2 is the amount of heat ejected into the ambient. So efficiency is equal to work output divided by W. Q1 is the work input. So here we have already calculated or derived the expression of turbine work and pump work in terms of enthalpies. So turbine work is H3 minus H4 and pump work is H2 minus H1, whereas Q1 is the amount of heat that is supplied into the boiler, so that is H3 minus H2. So that is an efficiency of a Rankine cycle when pump work is considered. So here we have considered the pump work. So the efficiency of ideal Rankine cycle when pump work is neglected, so that portion H2 minus H1 represent the work done. So isentropic efficiency of turbine when pump work is neglected is given by H3 minus H4 divided by H3 minus H2. So the question is then why we neglect the pump work, or why does not we consider the pump work when we derive or calculate the efficiency of a turbine. So the answer is in feed water pump saturated liquid enters, whereas in turbine saturated vapors enter. And for open system work is W is equal to V V2 minus V1. So that if you remember in the first slide, I have on the right side bottom, I have already written the value for the work expression for open system, that is W is equal to V into P2 minus V1. So that V is the specific volume, and the value for the specific volume for saturated liquid is very less, whereas the value of saturated volume for saturated vapor is much greater than the value of saturated liquid. So the value of specific volume for saturated liquid is much smaller than the value of saturated vapor, usually superheated vapor, because as I have already shown you in the TS diagram, the heat supplied in the boiler is as much so that the working fluid may enter into the superheated region. Therefore, W pump or work done on the pump is very less than the work produced by the turbine. That is the reason that when we are calculating the efficiency, the pump work is neglected. So some conceptual question answer. So which component determines the high pressure in a Rankine cycle? What determines the low pressure? So we have already discussed that the ideal Rankine cycle consists of two isobaric and two isentropic process. So here we have asked the components for high pressure and low pressure for Rankine cycle. The high pressure in the Rankine cycle is determined by the pump. The low pressure is determined as the saturation pressure for the temperature as you cool in the condenser. So high pressure, so high pump function is to supply pressure, whereas low pressure, so we have already studied about the saturation pressure and saturation temperature. So the phase change temperature is known as saturation temperature, and the pressure against that temperature is known as pressure. So as you know, the function of condenser is to change the pressure from to change the state from saturated vapor to saturated liquid. So the pressure against that phase change is known as low saturation pressure, and that determines the low pressure. So we have two pressure: high pressure pump and low pressure condenser. So the second conceptual question answer was that what is the difference between an open and closed feed water heater? So feed water heater is also known as the regenerator. The function of regenerator is to take energy from one part of the cycle and introduce it into the other part. So in the regenerator takes some of the energy from the turbine and that insert into the pump water that is entering into the boiler. So that energy is transferred to the fluid before entering into the boiler to raise its temperature. So it is of two types. In one type, the both the fluids actually mix together. So in open, they actually mix together, and in the closed feed water, they only exchange energy. So energy is exchanged only, and in the open, they physically mix together. So in closed feed water, it actually is somewhat like as a heat exchanger. So different fluid enter and they exchange energy and exit out without intermixing it. So in the closed feed water act as a heat exchanger, and open feed water is a mixture heater. So that is the home assignment for the lecture. All students are advised to go through example problems of each topic discussed in this lecture. So you must write a handwritten lecture summary report and email it to my email address, that is arsalan@ciitwa.edu.pk. You must keep the hard copies of every assignment, and you should prepare this lecture thoroughly, as there will be a viva and oral question answer session for every student before the commencement of next lecture. Thank you very much. Allah Hafiz.